In this video, following a short discussion on the principles of vibration and shock isolation, Daikon's semi-active air isolation technology will be introduced. The reason for vibration and shock isolation is to isolate a support structure from the vibration of an equipment installed on that structure, or isolate the equipment itself from the possible vibration and shock of the support structure. This is done by placing an isolator, which is some sort of a resilient device, between the two objects. The two traces on this plot show the measured vibration across a vibration isolator used to isolate a diesel generator. The blue trace is the measured vibration on the generator, and the red trace is the same measurement on the support structure. The isolator has drastically reduced the vibration transmitted to the support structure. The most commonly used vibration and shock isolation media are rubber, metal springs, wire rope isolators, and air springs, each with its own pluses and minuses. One major distinction between air spring and other types of vibration isolators is the adjustability of air spring. Placing multiple resilient devices underneath an equipment creates a multi-degree of freedom system with multiple modes of vibration and their corresponding natural frequencies. 4 vibration isolators are placed under an industrial transformer. The goal is to lower the transmission of vibration from the transformer to the support structure. Stiffness of the 4 isolators is selected so that the vertical natural frequency is set at 2.5 Hz. The geometry and inertia of isolated object as well as the placement locations of the isolators create multiple modes of vibration with their corresponding natural frequencies. Although isolation systems have multiple degrees of freedom, it is a good practice to start the design and analysis of such systems by viewing them as having only 1 degree of freedom. The goal of an isolation system could be isolating the support structure from the vibration of an equipment which is subject to a perturbing force. An example of such application is the isolation of an industrial fan with the objective of lowering the transmission of vibration from the fan to the floor. Alternatively, the goal of an isolation system could be to isolate the equipment from the perturbing motion of the support structure. Suspension of a vehicle is a good example of such application. The suspension system is to lower the transmission of the up and down movement of the tire caused by the unevenness of the road to the body of the vehicle where the passengers are. Transmissibility is the metric for judging the effectiveness of an isolation system. It is defined as the ratio of the transmitted force over the perturbing force. For systems subject to base perturbation, transmissibility is defined as the ratio of transmitted motion over the perturbing base motion. Transmissibility is frequency dependent. Its magnitude is large over low frequencies, small at high frequencies, and excessively large at the vicinity of the natural frequencies of the isolation system. Vibration isolation systems should be designed so that the perturbing frequencies fall in the frequency range where vibration isolation is effective. The objective of an isolation system is making transmissibility as small as practical over the frequency range of interest. Mounting an equipment directly on its support structure, the practice known as rigid mounting, is certainly an option exercised in some applications. The absence of isolators allows for all of the vibration and shock to transmit between the equipment and the support structure. Rigid mounting is normally practiced where the integrity of the installation is very important but the transmission of vibration is not. Note that the absence of isolators allows for the support structure to hug the equipment and prevent it from any motion. When lowering the transmission of shock and vibration is the goal, equipment should be resiliently mounted on their support structure. The flexibility of the isolators in such systems allows for small motion of the equipment. To avoid potential occasional large motions which could jeopardize the installation integrity of the equipment, the extent of motion needs to be managed by either incorporating snubbers to stop the excessive motion or lowering the isolation effectiveness by using stiffer isolators or adding auxiliary mass to the equipment. All of these motion management solutions have their pluses and minuses. The dynamic attributes of isolators, namely their stiffness and damping, have a profound impact on their vibration isolation effectiveness. Frequency response function of transmissibility is commonly used to judge the effectiveness of an isolation system. Note that the goal of any vibration isolation exercise is to lower the magnitude of transmissibility. Clear from the transmissibility frequency response, vibration transmission is mitigated at higher frequencies and exacerbated at lower frequencies. For this reason, the design should be done in such a way that all the perturbing frequencies fall in the high frequency region. Comparison of the red trace corresponding to the transmissibility of a soft isolator to the blue trace corresponding to the transmissibility of a stiffer isolator shows that the isolator with lower stiffness transmits less of the perturbation. As expected and shown in the motion frequency response, isolators with low stiffness allow for more motion of the isolated equipment, which will adversely impact the installation integrity of the isolated object. So, the stiffness of isolators are selected with the goal of having acceptable, but not necessarily ideal transmissibility without potentially causing excessive motion of the isolated object. The extent of damping in isolators affects both the transmissibility as well as the motion of the isolated equipment. The blue traces in these frequency response functions correspond to high isolator damping, and red traces correspond to low damping. The transmissibility over the frequencies of interest are lower and thus better for isolators with low damping. But again, the low transmissibility is at the expense of having a highly underdamped potential resonance. So, as in stiffness selection, isolators damping should be decided on, with a compromise between having an acceptable transmissibility and avoiding potentially excessive resonant motion. Random vibration and shock perturbations are normally intermittent and possess energy over a large frequency range. When such perturbations hit an isolation system, the isolated object responds in a transient fashion, mainly at the natural frequencies. Damping in such isolation systems lowers the extent of this response. The left plot shows the shock-induced motion of the isolated equipment, and the right plot presents the transmitted acceleration in an isolation system with two different damping levels. The following observations can be made from these plots. For random vibration and shock isolation, the isolators should be soft with sizable amount of damping. An example of such isolators is metal springs paired with viscous dampers, and to avoid having excessive equipment motion, the isolators should be stiff with high damping. Damped elastomers with short height is an example of such isolators. Passive isolation techniques cannot satisfy the above requirements without any compromise, and that brings us to controlled isolation system using adjustable air isolators. To avoid any compromise between isolation effectiveness and installation integrity, the parameters of the isolator need to be changed in real time depending on the nature of perturbation the isolation system is subject to. Air springs are the only isolators with adjustable parameters. In their uncontrolled state, air springs are soft with excellent vibration and shock isolation attributes. But this low stiffness could allow for occasional shock-induced excessive motion of the isolated equipment, which is undesirable. Air springs are also highly underdamped and thus provide excellent high-frequency vibration isolation. However, this very low damping results in poor shock isolation. Under the supervision of Dicons isolation control technology, air springs can change their stiffness and damping and thus provide excellent shock and vibration isolation at low and high frequencies, plus good installation integrity with small motion of the isolated object. The ability of Dicons control technology in changing both the stiffness and damping of air spring is demonstrated using a rather large spring mass system. A rather large 1 degree of freedom horizontal pendulum is set up to demonstrate the ability of Dicons control scheme in adjusting the stiffness and damping of an air isolation system. The demo device is made up of a 700-pound mass and an air spring with the diameter of 12 inches. The natural frequency of the uncontrolled 1 degree of freedom system is 2 Hz. The demo starts by having the system perturbed with the controller off. The response is almost undamped oscillatory motion with the frequency of 2 Hz. In the second run, the system is perturbed again with the controller set to lower the stiffness of the system. The slower oscillatory response is an indication of smaller stiffness and lower natural frequency. In the third run, the system is perturbed with the control first turned off, and halfway through the run, the control is turned on and set to add damping to the system. The recorded motion clearly shows the undamped response of the uncontrolled system during the first 2.5 seconds and damped response for the remaining duration. In the last run, the system is perturbed with the controller set to stiffen the system with no damping for the first 3 seconds and then adding damping to the system for the remaining 2 seconds. The recorded motion clearly shows the switch in the parameters of the air spring from stiff with no damping to stiff with sizable amount of damping. Note that in all these runs, the posture of the system is regulated, that is, the horizontal pendulum remains truly horizontal at 0-degree angle. As indicated earlier and seen in the demo, Daicon's controlled air isolation system adjusts the stiffness and damping of the air spring in real time, accommodating the conflicting requirements of an ideal isolation system. All of these while the height of the isolated equipment is being controlled to remain unchanged. As mentioned earlier, the unique feature distinguishing air springs from other isolators is their adjustability. This feature of air springs, i.e. adjustability in conjunction with proper software, allow for on-demand change in the states of the isolation system in real time, adapting it to the current applicable conditions. All of these are done without adding massive and bulky hardware to the system. As such, there is no weight penalty, which is important in marine and other automotive applications. Daicon's controlled air isolation system operates under the supervision of a computer which monitors the vibration of the equipment as well as the support structure and adjusts the states of the isolation system accordingly. Isolation systems that are soft and highly underdamped provide excellent vibration isolation. The ones that are soft and damped provide great random vibration and shock isolation. But to have robust installation with limited isolated equipment movement, the isolation system should be stiff with high damping. In many applications, all of the above conflicting requirements need to be satisfied. As such, passive isolation systems are designed by arriving at a compromise on all these requirements. Alternatively, low-cost microcontrollers, sensors, high-speed valves, and elegant control algorithms, along with the adjustability of air springs, can be used to deliver uncompromising isolation. By automatic switching of its parameters, Daicon's controlled air isolation system delivers uncompromising excellent isolation effectiveness against vibration, random vibration, and shock perturbations while maintaining the installation integrity of the isolated equipment.